So they show the formula as to how we get this change of base, or rather the proof of it. We have, let's say we have a logarithm with any base other than 10. Base 10 is, you don't need change of base. And you rewrite it as an exponent. So base exponent equals a. We just did this in bell work. If you take the log of both sides, you can bring this in front and then divide, and you'll see that the number you're looking for is actually the log of your original one over the log of your original base. And so here's the change of base formula. What this is saying is, in your calculators you have log. What is the base of the log in your calculator? 10, all right? Unfortunately, every one that you're going to get is not going to be base 10, or you could just plug it into your calculator. What this does is this takes your calculator, and now you can calculate your bases that are not 10. You pretty much use any log. So now we're going to say log base 10, and we are going to rewrite what we're looking for to a log base 10 formula. So for example, if you look at, let's say I wanted to find log base 4 of something like 13. Obviously, you're not going to be able to just do that in your head because 4 does not multiply by itself to get 13. So we can use this formula with log base 10. We're going to rewrite it, and we're going to say, well, that's the same thing as log base 10 of 13 divided by log base 10 of my original base 4. That will equal log base 4 of 13. So the log of the number you're looking for divided by the log of your base, using a common log or using, we're going to do natural logs later as well. All right, so that's what this change of base formula does. It helps us find bases that we normally would not be able to find. Let's look at the first example, example 1. This says solve 3 to the x equals 32. Obviously 3 to the x equals 32 is not going to be an integer, right? So it's going to be somewhere between, 3 and 4. But we don't know exactly what. And so what we're going to do is we're going to use change of base formula here. We're going to rewrite this as a log. So if we rewrote this as a log, the log would be a base of 3. So log base 3 of 32, and we are looking for the exponent. The problem here is we do not know log base 3 of 32. So for this portion, we are going to use our change of base formula. We're going to say the common log, log base 10 of 32, divided by the common log, log base 10 of our original base. That will equal log base 3 of 32. And then you can actually put that into your calculators. Now your calculators may open a parentheses, okay? So pay attention to order of operations. In your calculator, if it does this, you have to close it, then divide, and then log 3, all right? If not, it's going to keep it open, and you're going to have a log within your log, and that's not what you want. So when you put this into your calculator, round it to the nearest 10,000 is what we're going to do. That's 4 decimal places. You should get approximately 3.1547 as your answer. So how does this help us? We have something like this. We have 4x to the 5th, 4 to the x plus 5 equals 12. The problem when we have something like this is that exponent is actually where our variable is. And that's actually where we're solving. And so we want to do kind of the same process here. We want to get it out of this particular form. There's 2 ways to do this, okay? 2 ways to do this. So I'm going to show you both ways to solve this problem. One uses just the expansion like we've already done, and one uses change of base, all right? And so the first way that we are going to do this is we are going to just do expansion using our regular base 10. And they work out exactly the same. So if I wanted to just use log base 10 of both sides, log base 10, all right? Remember, whatever you do to one side, you can do to the other. So I've taken the log of both sides. I haven't changed my equation. It's like adding 3 to both sides. We're good. What this does is my rules for logs say anything in the exponent can become my coefficient. So I can take my exponent here and I can put it in front. So now I have x plus 5, that came in front, times log of 4 equals log 12. I'm solving for x. I can divide both sides by log 4. I have x plus 5 equals log 12 divided by log 4. And then my last step is to subtract 5. So x is going to equal log of 12 divided by log 4 minus 5. All right? When you put that in, you're going to get a negative number because of that subtraction. You're going to get approximately that's a negative, 3.2075. All right? Here's the thing. Bases cancel out bases. All right? They have to be like bases. So a base of a logarithm will cancel out a base of an exponent. The other way to do this is instead of doing log base 10, so log base 10 did not cancel out a base 4. All it did was it helped me expand. What I can do is I can actually take the log of both sides, but this time use a base 4. Log base 4 of 4 to the x plus 5, log base 4 of 12. If you have the same base log and the same base of an exponent, they will literally cancel each other out. And all you will have is the x plus 5. But over here you have log base 4 of 12. Here's the thing. In my calculator, I can't do log base 4 of 12 unless I go into the menu and change my bases, which is more difficult than change of base formula. So to solve this, I am going to subtract my 5, but to do this piece of it, I have to use change of base. What happens if I do change of base? Well, that's going to be log of 12 divided by log of 4, which is exactly what I had here. All right, so if you understand change of base, you can go straight from this step basically to that step, and it can be a little faster if you remember that you can just do change of base for this piece of it. All right, however you do it, whether you use common log of both sides and expand and divide, or whether you just do whatever the base is to cancel out the base, you're going to end up with the same answer. This is still going to give you negative 3.2075. All right, but there are 2 ways to do it. You can go ahead straight to common log, expand and divide, or you can go straight to the base that you're talking about. It will cancel and you'll use change of base there. So we have a half-life of 5730. This will always be your formula for half-life, okay? You will always have an initial amount times 1/2 to the time that it is cutting in half, whatever it is, the time that it is depreciating, if that were what it is, over the half-life itself. And then just plug it in. 18 is what we want, 19 is what we started with, 5730 is the half-life. We took the log of both sides. We expanded with our exponent. Our exponent came in front. Divide. Again, if you did your other base, you would end up with change of base right here. And then multiply both sides by 5730. Check your calculator work. Make sure your calculator work is correct. All right, let's look at the first one. So for this one, I'm going to take the log of both sides. So I have log of 1/2 to the x over 6 equals log of 2/7. I'm going to expand. So I have x over 6 times log of 1/2 equals log of 2/7. And then I'm going to divide and multiply. So I'm going to divide by this log. X over 6 equals log of 2/7 divided by log of 1/2. And then multiply by 6. So I get 6 times the log of 2/7 divided by log of 1/2. And you should be able to put that into your calculator. Just like that. A cesium-133 isotope decays from 60 milligrams to 12.25 milligrams in 12 hours and 15 minutes. What is its half-life? So our initial amount is this 60. What we end up with is this 12.25. Set this up like this. 12.25 is going to be equal 60 times 1/2 to the, and we have the time. The time is 12.25 divided by whatever the half-life is. And we're in hours, not years. So it should, this is going to represent hours. Let's do bases and bases. All right, so we have gotten rid of exponential bases using logs. The same is true for log bases. All right, so if an exponential base can be canceled out with a log base can be canceled out with an exponential base. So I have a base here of 27. I'm going to use that as my exponential base. So I'm actually going to put that as an exponential base on both of these. All right. What I'm saying is I have 27 to the log 27 of x, and I have 27 to the 2/3. All right. Bases cancel out bases. So the base of an exponent is then going to cancel out the base of my log. These cancel each other out, and I get x equals 27 to the 2/3. All right. 27 to the 2/3 is actually something you can do without a calculator. Because remember, the base here is my index. So x equals the cubed root of 27. And this represents my exponent squared. What is the cubed root of 27? 3. So x equals 3 squared. So x equals 9. All right. Bases cancel out bases. If you look at B, you cannot do this process until you only have one logarithm. All right. So here I'm going to have to use my rules about condensing. I need to condense it to one logarithm before I can use that process of base canceling out base. So what is my rule for logarithms? If I am adding two separate logarithms, how do I make them one logarithm? I multiply what's inside, 6 times x. All right, and now I can cancel this base out with a base. What is my base going to be here? 9. So I have 9 to that huge power and 9 to the 3/2. On the left-hand side, the base 9 and the log base 9 will cancel out, and I just have that 6x. On the right, I have, that is my root index, the square root of 9. That is my exponent cubed, all right? What is the square root of 9? What is 3 cubed? Is 27. So I have 6x equals 27. What's my last step here? Divide by? All right, and can I reduce it? What goes into 27 and into 6? Yeah, so I can divide top and bottom by 3. I'm going to get 9/2 here. These are actually the same type of problems. What is my base, though? 10. All right, so there are going to be times when it doesn't show you a base. That is an implied common log. And so you're going to do these exactly the same way. You're just going to take 10 to that power. On the left-hand side, the 10 and the common log cancel. You have x equals 10 to the 5.37. This you will do a decimal, by the way, because this is not going to be an exact number anyway. In your calculators, you do have a 10 to the power. If you look on your calculator, your log key typically has 10 to the x above it because those are inverses of each other. And so you can do that, or you can just do 10 with a little caret top and 5.37. You should also have this button on your calculator as well. They mean the same thing, all right? If you use the 10 to the power on your calculator, it's going to automatically do it and put it in parentheses for you, or you can just do your power button on your calculator. Either way, you do have a pretty large number here. They rounded to the whole because it's such a big number. All right. Yeah, so pretty big number there. Conceptually, the one on the right is the same as the second one we just did. They, again, have the same base. They're common logs. I am going to do something with this first, though. What am I going to do with that 2 when I start condensing? Yeah, this is going to go in the exponent of that x. So I have log of x to the second power plus log of 4. Now I'm going to condense this to 1 log. Addition means that I condense to 1 log with what? Multiplication. I'm actually going to say 4x squared. Order does not matter when it's addition because it's multiplication. And all of that will equal 2.5. Now I have 1 log. I can get rid of my log. Base cancels base. So I can say 10 to this power equals 10 to the 2.5. 10 and common log cancel. 4x squared equals 10 to the 2.5. What do I need to do next to solve for that x? You go ahead and divide by the 4 first and then do the square root. You could do it either way, but you'd end up with a 2 in front and have to divide, and that usually causes more errors. So we're going to say x squared equals this right here. And yes, we do take the square root. All right. In your calculator, you can actually do all of that. You can open your square root. It will open a parentheses. You're going to say 10 to the 2.5. Make sure you close that parentheses as well. Divide by 4. Close the parentheses again for the square root. And we're going to talk about this right here. You should get approximately 8.89 here. What happens when I take a square root with a variable, though? Positive and negative root, right? Here's the thing. You have to check these, all right? Because if I were to plug in a negative number right here, I'm saying 10 to what power equals a negative number. It's not always true that the negative is not going to work, but in this case it is. Because you can't take 10 to any power and make it negative. So your negative here is extraneous. X is only going to equal the positive 8.89. If this had been in parentheses x plus 11, the negative 8.89 would be fine because negative 8.89 plus 11 is still a positive number, all right? But if you plug it in and what you're taking the log of is a negative number, we have a problem. It's extraneous. It does not work. All right? And so the only answer that works here is your positive number.